Okay, apparently we are short of a herald, so I'll just step in. Let me introduce you to Travis Goodspeed, who is a very interesting and resourceful MSP430 hacker. And he will show you how to start embedded development with very few financial with very few money, and hopefully that will be very interesting, and you can start doing your own embedded development right after this talk.
Howdy. So in this lecture, I'm going to show you how to take apart a $20 Introduction to Microcontrollers kit from Texas Instruments and rewrite the software not of the target board that you're supposed to program, but of the programmer itself. So in doing that, you have to copy out the existing software and reverse engineer it sufficiently to understand what has to be in the replacement. So to quickly review, the MSP430 is a 16-bit microcontroller. It's von Neumann architecture, and it has a table of interrupts at the end. So wherever you have like a callback from hardware or an event that's fired when, say, a pin rises or a byte comes in over a serial port, the microcontroller just looks at an address at the end of memory and pushes it into the program counter. I did a hack of the bootloader of this chip, allowing its password protection to be bypassed. And in this case, they actually wrote their own bootloader on top of that. So in addition to the bootloader that's in permanent mass ROM, there's also one in flash memory. So when I say bootloader in this lecture, I'm not referring to the same thing as I did in my day one lecture. And also, a microcontroller doesn't have a real operating system in it. So instead, you have individual memory mapped addresses that you write to affect the outside world. So you can change pull up and pull down resistors on an I/O pin. You can change that pin from an input to an output. You can pull it high, pull it low. And there are also clocks and timers and such that you can access by peeking and poking individual addresses. And when you do this, you're not calling a function that exists elsewhere within the chip. You're just writing to an address, waiting a bit, and then reading from another address, or waiting for an interrupt to fire. This is the device that we'll be hacking. The piece on the left is the target board. It's about the size of 1 euro cent, and it has the MSP430 F2012 or 13 on it. There's also an LED and the pull-up resistor and the decoupling capacitor and all of everything you need to have a functional device. But it's small, and it doesn't have much power. It only has one serial port. It can only do so much. And while it's fun to play around with, I'd rather have an advanced project out of this. And I'd rather have a reverse engineering project out of it. So I took the right side of this, which is a JTAG in-circuit debugger, and I dumped its firmware. And I reverse engineered it, as well as the USB to serial section of the board, which behaves differently. Another target board that you can have, the intended route for you to move up with TI, is this. It's a 2.4 gigahertz wireless sensor node, powered by the same connector, and running firmware that they supply for you. Now on the EZ430, if you read the documentation, you'll find the JTAG pins, and they exist as test points on the side of the device. So if you build an adapter, you plug it up, you can then hook up another in-circuit debugger from TI, and you can dump all of the code from the target device. You can also replace the code. And the initial motivation for dumping this was to gain Linux support on the radio version of the board, which is red. Its firmware is incompatible with Linux. And you can either run it through VMware, which isn't terribly reliable, or you can copy the firmware from the blue board into it. And you do this with GDB. So you just load up GDB connecting to the target, and then you say dump memory, ihex, and then the file name and the address range. You start at 200 and you go to 1000 hex because everything beneath 200 is I/O. And if you read or write I/O, you cause unintended side effects elsewhere in the system. So reading from it isn't terribly damaging, but if you were to dump all of memory and then write it back into another device, you would change the clocks and you would actually break the JTAG session. The schematic diagrams for this are freely published by TI in an application note, SLAU 227. They're all unique words, so if you Google for that, you find no other document. They don't present well on stage, and I suppose there aren't handouts here. But if you have the slides, you can look at this diagram. And it comes in multiple pages. So here we have the MSP430 along with the programming port, J2 on the right. It's here. You have series resistors and all of that stuff. And then there's a USB to serial chip, the TUSB 3410, which is similar to the FTDI chip, many of you will be familiar with. And there's a serial EEPROM, the CAT24FC16UI. Sometimes that part number varies. It'll be a larger EEPROM. But the idea is that firmware for this device resides entirely within the MSP430, which is the CPU of the device, and also within the CAT24 EEPROM, which provides firmware for the TUSB 3410, which is a USB to serial chip, and it's also a CPU. It has an embedded 8051 core, and the reason why the red version of this board won't work in Linux is that instead of using the native USB to serial mode of this chip, TI wanted an extra serial port. So they wrote custom 8051 code, and then matching software on the PC end to allow them to have 2 serial ports from a chip that in hardware is only supposed to give 1. So these are the 3 main chips of the board. You've got the MSP430, the CPU. You also have the TUSB 3410, which is a USB to serial chip and also a CPU. And then you have the CAT24C32, which is an EEPROM and contains the code for the 3410. In hardware, they're connected like this. You have a single I to C bus between all 3 of the chips, and then a UART that only runs from the 430 to the TUSB. So to dump the code, I took 2 hypodermic syringes running to an I2C adapter. And the nice thing about I2C is that it's multi-master. So when I plug these syringes into the board, and I've got the board plugged into the USB port, I can actually dump the code of this chip on the same bus that's being used by the actual chip in operation, and there are no collisions, there are no errors. I get a clean dump of the chip, and the operating system doesn't throw any errors or complain. So in the classic version, the EZ430F 2012, there's nothing interesting inside of the EEPROM. It says Texas Instruments and Unicode, and it has the basic configuration requirements for the USB to serial mode of the target chip. In the EZ430 RF2500, the Zigbee version, it actually contains executable code, and it prohibits updates over the USB port. So not only can your computer not only can your Linux machine not speak to it and get a serial port, but it can't instruct the chip to use the firmware that it has within the Linux kernel, the binary blob. And they do this to provide the 2 UARTs. The hard one goes to the onboard MSP430. This is how your computer talks to the debugger. And there's also a soft one to the target board so that when you have the Zigbee node plugged in, you can send commands to it. You can say, transmit this packet or send me packets. The soft UART is horribly unreliable. So if you intend to use this in a commercial application, be sure to construct a line-level serial port, such as out of a TUSB chip, an FTDI chip. So I dumped the firmware of the MSP430 and I ran it through an analysis tool that I've built called MSP430 Static. Firmware analysis tools, or I suppose it's not firmware in the 32-bit range. So on a PC, you have IDA Pro. And IDA Pro uses lots of very sophisticated algorithms to search in anything approaching a reasonable amount of time. On this chip, all of memory is 64 kilobytes. 32,000 instructions is the absolute maximum. And so you don't need these advanced, fast algorithms that make IDA Pro possible. You can just throw everything into an SQL table and do queries on it. So in 2 days, I wrote this analysis system in Perl, and this whole graph is done by a couple of SQL queries. Everything in red is a number other than 0 or -1. Everything in white is a 0. You'll note that RAM is zeroed out toward the bottom because that's what RAM does when it's reset. Flash memory resets to 1s. So you reset the entire sector to 1s, and then to write a byte to it, you move individual bits from a 1 to a 0. So all of the flash memory at the top that hasn't been initialized is in black. It's a bit hard to see, but at the top right, there's a bar of green, and that's the interrupt vector table. And then at the top right of the black region beneath it, there's a line of blue. We'll get to that in a minute, but note that it's exactly where the green bar is, just a little bit lower. And then I can draw a call graph. I can instruct it to dump a graph theory directed graph of every parent and child function. And you'll note that the spaghetti on the left is connected. There's no function that isn't reachable from somewhere. So it's all tied into one large structure. While on the right, everything is also connected, but it's a lot smaller, and it's not connected to the left region. And the reason for this is that you have two programs in this chip. So this thin band of red at the top is the structure on the right, and the lower region is the mess on the left. And then to zoom in on the interrupts table, you have the green interrupt vector table at the very top. That's 0x FFE0 to 1,000 hex, 10,000 hexes. And then beneath that, you've got the blue region, which is for proxying interrupts. It's a second interrupt vector table for the lower unit that's not implemented in hardware, but is instead implemented by proxying functions. So at the bottom right here, we have the IVT as a circle, and then all of its handlers come out from it. And those will handle things such as an incoming serial byte. And you'll note that only one of them actually calls another function. And that is too small to read, but that's init. Okay, so then init calls main, which calls configure, and these names had to be written by hand after the code was reverse engineered. But only one of the interrupts actually calls anything, and that is the interrupt that is executed when the chip is turned on. And then this code here is used to fetch serial bytes. You've got get byte, which is called many times from the get command function. Put byte is when bytes are written over the serial port, and this is for a sort of wake-up initialization with the PC. So when you start GDB proxy, so that you can debug the target board, before the actual JTAG debugger software is run, this code is run, and it's here that updates are read into the device. So it quickly checks over the serial port to see if there's new firmware, and if there is, you can load it through. To identify functions, you can't use symbols because they don't exist inside of the chip. If you were on a PC, you would have DLLs with indexes. You might have debugging symbols left in by the author. None of that stuff exists within the chip itself. And doing it by hand is too slow for the large number of functions in the smaller image. On the upper one, it's small enough that you can go through by hand and find each one and read it. I also have support for software that does this by hash. So I take all of the bytes of the function, I strip out pointers, and then I do a one-way hash function, and I can publish a table of those hashes with my reverse engineering tool. And then if any of the functions that you have exist within that database, it can recognize them. Unfortunately, this doesn't work if you're analyzing something new or something made with a compiler that you don't have access to. And the latter was my case. This software was written with a compiler that I don't yet have symbol importing working for. So another trick that you can do is to recognize it by port. And doing this is looking for the global address of a port that you know interesting code uses. So for example, there's a serial port, and there is an address that you write a byte to have that byte come out the serial port. So all you have to do is look for that address, and you get all of the functions that write serial traffic. The same for reading. So you can do a select statement in SQL, and you can get just a list of the functions that write out to the serial port. And usually there's one or two of them, and they're both put byte. Now, the loader itself is one of two halves of the, it's composed of two halves. So when you first power this device up, it quickly makes sure that all of the ports are correctly initialized. Because if you have, say, an input and an output next to one another, or you accidentally have a port and output mode when it should be input mode, you can tie up a bus. And if you don't configure the I2C bus properly, then you break it for everybody, and then the USB to serial chip can't function. So if you were to just write a simple blink the LED firmware image and place it within this chip, the board would cease to function on the USB port. Following this, there's a main loop, which accepts the update and eventually jumps to the entry point of the lower firmware. And because it configures all of the I/O and the clocks and the interrupts and everything that we need to have the device working, it makes sense to keep the bootloader at the top and just link it into our own custom firmware. So this is an example of the code that actually initializes a port. And the P3 cell, P3 out, P3 dir, they select which function the port 3 will be used for, which direction it will be used, as well as what its output values are. So like bis.b, bit immediate set byte-wise. So it sets the 16-bit of port 3 high. Rather than reverse engineering all of this code and marking out exactly which ports should be set high, which should be low, it's easier to just copy everything over and link in elsewhere. So you don't have to convert from this to the equivalent C, and then from C to identifying it on the schematic, and then from the schematic to the intent that the programmer had. You can do SQL queries to identify these, though. So this selects all assembly code where an address less than 100 or less than 200 is used. This gives you every access to every port, and then you have a table on which you can compare the ports. And the interrupt proxying is performed by handler functions. So, for example, the DMA access interrupt occurs at 0xFFE0. So at that address, there is a 16-bit word that is the address in memory that execution should flow to when the interrupt fires. And the handler is at FB78. This could be anywhere within the upper region. But it branches to the contents of F70. So for almost every interrupt, there's only one exception, it just takes the address that everything should be at, and it subtracts a couple hex from it. So FFE0 becomes F7E0. FFE2 becomes F7E2. So if the native address is in the FFE0 to FFFF range, the proxied address will be in the F7E0 range. And on the red version of the firmware, this region is actually slightly lower because it has a more complicated bootloader. But The infuriating thing about this, and what took me a week to notice, was that the reset vector is not among those that is proxied. And while flash memory begins at 2500 hex, this is where the chip begins to execute after it exits the bootloader. The interrupt vector table entry for the reset vector is ignored, and instead execution jumps to 2502 hex. The first word of flash memory is always left empty, and execution always begins on the second word of flash memory on this firmware image and only this firmware image. If you look at any other image from any other compiler, execution will begin at the very bottom of flash memory. So at this point, we know that the loader stage exists from F800 to 10,000 hex, that it proxies the interrupt vector table, but it doesn't itself use interrupts. So it can't have any event-based programming. It can only sit within a tight loop. And we know that it configures the ports and the clocks properly so that the chip can function and the bootloader can speak to the PC. We also know that the application stage is supposed to go from 2502 hex to F7FF, and that the interrupt vector table is supposed to begin at F70. So we can write a new GCC target. And in GCC, there's a linker script, or a .x file. There's one per family member, so you link differently for each chip in the series. And this is done because different chips have different amounts of memory and they begin at different places. You might want a firmware image to exist for a chip that doesn't exist. Because you might want to compile a single image that will work on multiple MSP430s and not care which chip is sourced during manufacturing. So taking advantage of this feature, I moved the text region, which is where executable code exists, from 2500 to 2502, and then I reduced its length so that it no longer collides with the end of memory. The data region is RAM, and I left that unchanged. Then the vectors I moved down to F70. And the bootloader and info memory and such are ignored by the compiler. I also had to crop the bootloader out. The nice thing about the Intel hex format is that each line is actually readable text. It contains a length, a starting address, and then the data. And you can just crop out the lines that you don't like. So a quick Perl script can say, give me this firmware image, but only in this memory range. So I cropped it out. You'll note that there's still some blue lower in the image, and that's because blue doesn't refer to data that's actually in the image, but data that's referred to in the image. So the blue band beneath the interrupt vector table is a region of memory pointed to by the proxied IVT. Then you compose a makefile, and in the makefile you specify which CPU and which linker script with the -t argument. Then you copy it to an Intel hex file. You crop off the last line of the bootloader. So then you can use the cat function to concatenate the two together, and that gives you a single firmware image that you can write to the chip that contains both Texas Instruments bootloader and your application software. So then, as it stands, I've brought this to Hello World. You can compile an image, you can write it onto an EZ430, and it runs. But I haven't made any utility out of that. So the next step would be either to build something out of this, to make, say, an I2C SPI adapter, like the Bus Pirate. If you look at the Bus Pirate, it's from Hackaday. It's a PIC microcontroller and a serial adapter. And then the PIC microcontroller does bit banging on any protocol that you specify over some GPIO pins. Well, this could do the same thing because it exposes its GPIO pins. It also exposes line-level serial if you need to do fast communications with, say, a Zigbee radio. This is also useful for side-channel timing attacks, as I did in my first lecture of this Congress. So you can write a program that runs on the ez430 and has immediate access to the hardware pins. It has no latency. It's the same as the old parallel port bit flipping stuff, except that we don't have parallel ports anymore, and they were never that good to begin with. The other thing you can do is reverse engineer the actual JTAG standard for the MSP430. Because while they've published enough to tell you how to program a chip, the documentation hasn't been updated in quite a while, and it doesn't specify how to program the new 20-bit chips, the MSP430X. So you could modify this device to, say, spit out debugging information, to do things like that. And you can add support for proper JTAG, whereas it only supports SPI-by-wire, the 2-wire JTAG standard. This is a commercial I2C adapter called the Aardvark from Total Phase, and this is the one that I used to dump the I2C EEPROM from the ez430. You could easily make a compatible product to this, and you could do it with a device that you can buy for $20 US. In the timing attacks, you send serial traffic with the start bit early, and then you can actually watch how long a password comparison takes within a victim chip. So for about half of the MSP430s, by doing this, you can figure out how correct a password guess is in like how many bytes out of your guess are correct. But to do this, you need absolutely low latency. If there's a context switch caused by the preemptive multitasking of your PC, then PC software that's trying to bitbang this will fail. On a microcontroller, you have no such interferences. You can write an application that runs on the board and behaves exactly as you instruct it with no operating system to get in the way. This is the second generation of the password cracker. As for reverse engineering JTAG, the documentation tells you how to program it, but it doesn't tell you how to debug it. You can't, by the documentation, single step the chip or set a breakpoint or do any of those things that are necessary in a proper debugger, even though the hardware supports it, even though TI's tools support it. So your only option is to use the closed source tools, a closed source proxy for GDB and such, or you can reverse engineer it. There's work in progress to break this that I'm not the primary author on, but I can refer you to it if you're interested. This is the recording that I took of JTAG. And we have a tool now that the guy who's doing the JTAG reversing authored, which can actually parse this. So you can spit out from this recording a list of read and write commands to memory. Soon breakpoints will be supported as well. What would also help would be able to identify this within the code. So instead of looking at the line level recordings and writing tools to identify them and such, you could identify the JTAG IO functions which are within the TI implementation of this. So there's instruction shift, data shift, set TCLK and clear it, and that sort of stuff. There aren't many functions that act as the primitives for this sort of stuff. So if they can be identified within the firmware image, you could write a script for the reverse engineering tool that runs through and identifies, say, every instruction that might be shifted in. And then you've got a list that you can check off in your recordings. So if you know that, say, 37 instructions exist, then if you found 35 of them, you know that 2 remain and you know which 2 remain. So are there any questions? Yes?
How did you get the sniffing over the JTAG? You just connected to some kind of probe or something, and
Yes. So this recording is from an FPGA that has been reflashed with a bitstream to make it behave as a logic analyzer. And then the software that you see connects to it through a serial port. When you push a button, it does a quick recording at up to 100 megahertz. And then the recording gives you the logical value of each pin at each moment in time. This is also available in a text file that can be parsed by script.
So, and can you buy this on
Yeah,
in your
this
shop,
is
or?
a $100 student FPGA development kit with free software that I believe was written in Germany. SUMP's logic analyzer. Any others? Okay, so let's see. Okay, so after this lecture, I'll be doing a short workshop on the ez430, and I can bring out the code and we can look at it and attempt to find new things that I have yet to find myself. And then in the third round of lightning talks, I don't know whether that's tonight or tomorrow, I'll be presenting CMOS gates that I've made into the shape of Tennessee to be neighborly. So please come to them and meet me in private if you have any questions. Also, there will be a lecture on RFIDs later this evening. And following that lecture, devices for programming RFIDs, which use the MSP430, will be sold at cost for a workshop tomorrow afternoon. So. Oh, yes?
Shouldn't there be an entry point from the interrupt vector table, from the init function, also to the main loop?
Yes, I'll load that up. Here we go. This one. So you have the interrupt vector table here. And then all of these orphan functions that are just squares that don't go anywhere, those are proxied to the lower firmware image. The only exception is init, which then calls main directly. And this is like a function call. If main were to return, it would fall back into init. And then somewhere in that maze, there's an instruction that just pushes 2502 into the program counter. In the case of the lower image, though, looking at the zoomed-in version, you see blue for each entry of the IVT that's actually red. So if you have a literal pointer inside of an assembly language instruction, from anywhere in the program to any other place, it's a blue block. And you see blue blocks for everything except the far right of that line. And that's the reset vector of the lower image. So while FFFE is used at the top to begin the bootloader, F7FE in the lower bootloader is ignored. Instead, the value is hard-coded elsewhere within the red image. Any others? All right, thank you.